This is the AP exam review for our Chapter 15 test. Let's go through a few multiple choice questions. Let's take a look at the one on the left, number 46. A 1 mole sample of X and 1 mole sample of Q are introduced into an evacuated rigid 10-liter container and allowed to react and reach equilibrium at 50 degrees C according to the equation above. So here's the equation. We have 1 mole of X, 2 mole of Q, and then 1 mole of R, 1 mole of Z. Our Kc looks like a high number, so we'll consider that. At equilibrium, which of the following is true about the concentrations of the gases? So we're beginning with 1.0 mole of this guy and 1.0 mole of our second reactant, and we reach equilibrium. Now remember that as we go toward equilibrium, some amount of this will be lost and a good amount of this will be made. How much? Well, the ratio is given to us by Kc. Because we see this is a big number, we know that products over reactants must be a pretty high number, which means we have a lot of products and a little bit of reactants, and that's how we get to this huge number, 13,000. So let's see at equilibrium what matches. A says that R will be half as big as Q, so it's saying that R will be less than Q. This is not true because we said R is a product, which means we have a lot of products. Don't get confused by the fact that this R is the same as this. This means reactants. Here. So this is incorrect because, in fact, we have quite a bit more R than Q, and we don't have half as much. B says Q is 1/2 of X, so it's actually saying that the amount of Q is half the amount of X. Now, according to the stoichiometry, it is related 2 to 1, but X is actually 1/2 of Q. So this is wrong because it's backwards. Think about it. It actually says that Q is bigger than X. Here it's saying Q is less than X. C says R is equal to Z, which is greater than Q. Now R is equal to Z is correct because for every 1 mole of R we create 1 mole of Z. So this is right. And it is bigger than Q? Yes, because Q is a reactant and Z and R are products, and we have a lot of products according to the equilibrium constants. This is the correct answer. And certainly D is incorrect because it says everything is equal. If everything is equal, likely the constant will be close to 1, and it's not, so that won't work. Okay, how about we take a look at the question on the right. A similar reaction, we have 2xy becoming x2y2. We have a Kp that's pretty high, and it says the reaction decomposes and is represented above. A sample of each of the 3 gases is put into a previously evacuated container, which means we only have reactants. I'm sorry. We have all 3. Apologies. We have all 3 of these in the container. All 3 are placed into the evacuated container. The initial partial pressures are shown in the table below. So these are the amounts. Now these are initial and not equilibrium. And they're asking us the temperature of the reaction is held constant. In which direction will the reaction proceed? Toward the products or toward the reactants? Well, this is a case of calculating where we are at now if we put all these into Q, which is defined as products over reactants, the same exact way as K is. We'll see where we're at, and we'll compare it against our K. So, having products over reactants, we get ourselves, let's do it on this side, we have Q equal to XY is our reactant. That will go on the bottom. That'd be 0.01. Now that is squared because of the 2 in front. On top we have 0.2 and 2. Now if you do this calculation, you'll come up with a really big number, something I think like 4,000, something like that. So, and you can go ahead and try it because we have 0.4 up here, get 0.4 at the top, and we have a 0.001, I believe, which is, we'll move this 4 times, yeah, this should get us the number. So if this is the number, then Q is actually huge. Q must decrease. In order for Q to decrease and get to K, we have to form less products, more reactants. So in fact, the equilibrium will shift left. Remember our little trick, you can list K first and then Q according to the alphabet. And because K is less than Q, it'll shift left. So the reaction will form more reactants. That would be the right answer. Okay, let's take a look at the next few right below. Oh, that'll work. So number 40, we have calcium carbonate, which is a solid decomposing into another solid and carbon dioxide gas. Delta H is given to us. Now this is endothermic, so let's think of heat as a reactant right away. The reaction system represented above is at equilibrium. Which of the following will decrease the amount of CaO in the system? We're looking at the product here. What will decrease the product? A says increasing the volume of the reaction vessel. If we increase the volume, that affects pressure. Pressure would actually decrease. So if pressure decreases, now pressure is on the right side. We have gases on the right side, no pressure on the left side. So if you decrease the pressure the system will try to increase the pressure by shifting it to the right, therefore making more CaO. We don't want that, we want less. It's asking for which will decrease. B says lowering the temperature of the system. Now by lowering the temperature, I'm technically removing heat away from the system. If I remove heat from the system will shift left to create more of that heat, therefore taking with it CaO, reducing CaOs. So this is actually the correct answer. Now C, by the way, says removing some carbon dioxide. If you remove carbon dioxide, it'll shift right again, making more CaO. That's not what we want. Removing some calcium carbonate, solid, won't do anything because remember, solids do not affect equilibrium. So this won't do anything either. If we take a look at the right, a very similar question. Here we have the dissociation of weak acid HF. Acids we're going to study in more depth in the next chapter. But as of now, just treat this as an equilibrium system. Looks like we have the equilibrium set up here. Adding a 1 milliliter sample of which of the following would increase the percent ionization of HF in 10 milliliters of a solution. So we want to maximize this reaction. Increasing the ionization of HF. HF here actually gets ionized, which means it gets split up and become ions. So we're asking which reaction will force the system to the right. That's really what we're asking indirectly. Now if we increase Kf, what Kf does, now you don't see K anywhere in here, but Kf brings our fluoride ion into the equilibrium. So if we increase the amount of fluoride ion, the system will actually shift left to remove it. Remember, equilibrium always does the, Le Chatelier's does the opposite of what equilibrium is doing now. B says increasing some H2SO4. Now you don't see H2SO4 in here anywhere. This is another confusing point. However, this will increase the amount of H+ because we're adding both of these. Now H+ is the same thing as H3O+. You may recall this from the acid chapter. If not, just kind of believe us. We'll reiterate this. In fact, the way what happens is H+ teams up with a water molecule to produce this hydronium ion. So in effect, we're also increasing H3O+, which will shift the system to the left. That's not what we want. So these two are out. If we increase HF, hey, that looks right. If I increase HF, that's a reactant. That will shift it to the right, increasing the ionization. So this should work. Incidentally, distilled water won't work because distilled water is a liquid. Remember that liquids do not affect equilibrium. That one's out. Okay, let's take a look at the last question here, which is sort of a free response question, which means we have to write some equations out and so forth. So here we have two compounds along with their Ksp values. Now remember, Ksp deals with solubility. These values tell us how soluble these compounds are. They are insoluble because hydroxides are technically not soluble. So the Ksp values for both of these are given above. A 1 gram sample of powdered Fe2O3 and 1 gram sample of aluminum oxide are mixed together and placed in 1 liter of distilled water. So we're putting both of these guys into a big container. 1 gram of each. 1 gram of this guy, 1 gram of the other. I says which ion, Fe3+ or Al3+, will be present in higher concentration? Justify your answer with respect to Ksp values. So because Ksp is the solubility product, it's actually how much products you have in the solution. Remember, Ksp refers to the fact that FeOH is dissolving into Fe and OH. So it's actually dissolving. So the higher this number, the more products we have. Because the higher number is actually for aluminum hydroxide, this number is higher than this because of the power. This is about 1,000 times higher than this, a little less than 1,000. But because aluminum hydroxide's Ksp is higher, we'll have more aluminum present. And that's the idea. So Al plus 3 because Ksp is higher. And that's the idea. 4AlOH3. Double I says write a balanced chemical equation for the dissolution reaction. So we want to show how aluminum hydroxide dissolves, and that's easy enough. That's actually what we kind of did up here, but for iron. So aluminum hydroxide is a solid, so go ahead and put these state symbols. Dissociates, and it's an equilibrium system, into aluminum 3+, which is aqueous, and hydroxide minus, which is aqueous. You'll have 3 hydroxide minuses for every aluminum. So this is the balanced equation, along with the state symbols. Finally, some students are asked to develop a plan for separating aluminum oxide from a mixture of powdered iron oxide and powdered aluminum oxide using chemical reactions and laboratory techniques. This is actually just the first step of a bunch of questions that I cut off, so we'll just take a look at this one. One student proposes that aluminum oxide can be separated from the mixture by adding water to the mixture and then filtering. I'll explain why this is not reasonable. Now, if you simply add a bunch of water to the mixture, so instead of doing it this way, if you have the mixture and just put a bunch of water into it, it turns out that we'll say that the mixture is half aluminum. We'll say that aluminum is blue. We'll say that iron oxide, hydroxide is red. What will happen is you'll get in the solution a little bit of each. Now, we said that aluminum has a higher Ksp, so you will get more aluminum than you will get iron, quite a bit more, but still you can't separate them that way because your filtrate will have both of these. There's really no way to separate because they're both insoluble. They just go both into solution, at the by different amounts, but they are both present in the solution, and that's why it will not happen. Okay, so think through these, try them on your own, and we'll put maybe a few of these on our test. This concludes for us our review lesson.